Greetings and welcome, internet friends. Mr. Waddy here, Algebra 2.10.01, talking about sample spaces and probability today. So a probability experiment is an action or trial that has varying possible outcomes. The possible results are called the outcomes, so that all possible situations or scenarios that could arise are the outcomes. For rolling a six-sided die, there are 6 possible outcomes. Collection of one or more outcomes is called an event, and such as rolling an odd number, right? So you're kind of defining a narrower set of possibilities. And the set of all possible outcomes is called a sample space. And so here, the first thing we're going to do is talk about finding the sample space. And so here we've got 2 different events taking place, and I'm going to draw a tree diagram as a way to quickly identify those things. And so first thing is flipping a coin, and so that branches out in 2 ways in which I could get, I was just going to put heads or tails and then heads, and I think everyone traditionally says heads then tails. I believe so. Maybe it's alphabetic, who knows. So heads and then tails are the possible outcomes of that event. And then rolling a 6-sided die. So this branch is supposing I got the heads outcome. And now I've got 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6 are the possible outcomes. And of course, 2, 3... I didn't give myself enough space here. 1, 2, 3, 4, 5, 6. There we are. And so here's my little tree diagram. And so if I want to know the total possible sample space, it would be done by counting all of these, of which the possible outcomes are represented by any path along this tree. So I could get heads and then a 3. I could get tails and then a 1. And then the total sample space is, 12 total things occurring. It is also possible to list them out kind of like this way, where I could have heads with a 1, heads with a 2, heads with a 3, etc. And then I could have, tails with a bunch of things as well. 3, 4. I guess I'll show some of them. So I would have had 1 through 6 with H, and then 1 through 6 with tails, and I would have had the same number of 12 possible outcomes. And so that's the first thing we've got to be able to figure out, is what's the possible outcomes, what is the sample space. Let's see, if I flip 2 coins, so coin 1 would be heads then tails, and then coin 2 would be heads or tails. And so that could, there are 4 possible ways this scenario could have played out, right? I could have had tails and then heads. I could have had tails and then tails. Then later on we might even get into scenarios of like describing what number of outcomes had the same flip for both scenarios, and so that would be heads heads or tails tails. And so 2 of the 4 outcomes, half of the time, you had the identical matching sort of thing. Boom. I'm gonna keep rolling because I've got, I think, 6 examples to talk about today. So for probability, there's theoretical probability, in which, well, first of all, let's talk about, that doesn't actually show up until down here. The probability of an event is the likelihood or chance that the event will occur. So a 0 for probability would be a certain impossibility, I guess. It's never going to happen. 1 as a probability is guaranteed to occur. And then numbers in between there, which you could represent as fractions or decimals or percentages, are the likelihood of that event occurring. So a 1/2 is equally likely to happen or not. Smaller is less likely, greater is more likely. The outcomes for a specified event are called favorable outcomes. If, right, you're trying to specifically flip heads, right, that would be your favorable outcome. Or successes. The outcomes are, when all the outcomes are equally likely, then the theoretical probability of the event can be found using the following. The number of favorable outcomes, which I'm going to use green for, all right, number of favorable outcomes divided by the total number of outcomes. Notice the denominator is not the number of unfavorable outcomes. No, it's the total number of outcomes. And so that will be our theoretical probability. You can also write it in some of this almost like a functiony notation, P of A. So the probability of A happening, and A isn't necessarily going to be a number. It could be probability of heads, right? Could be something like that. So it can actually have language there. So here we go. Finding the theoretical probability. A student taking a quiz randomly guesses the answers to 4 true or false questions. What is the probability of the student guessing exactly 2 correct answers? And so I could do a tree diagram. I could write this out. Let's see. Well, there's also a way to do it kind of like as a table. I'm a fan of actually using spreadsheets to generate sample spaces rather than doing so much writing. But well, let me write it this way. How many ways are there? In order to figure out probability, I need to know not just the number of ways to get 2 correct. I need to know the total sample space, the total possible outcomes. And so for 0 correct, that would be, right, false, 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 false. For 1 correct, I could have true and then false, false, false. Or I could have had false and then true, false, false. Or I could have had false, false, true, false. And the last scenario would have been this. So it depends, you know, notice these are considered different outcomes because which question they got correct varies. Here I could have had, right, true, true, false, false, true, false, true, false. And this, if you've ever taken tips with me, or later on you might, this is called a systematic list, where I'm trying to do an organized way of this. And so notice these 3 scenarios all had a true as the first outcome. Then I could have false as the first outcome. False, true, true, false. False, true, false, true, which is different than that one. Yep. Or false, false, true, true. All right. And so this actually, I did just identify exactly 2 correct answers. There are 6 outcomes there. All right. That give me exactly true. And then let's see, for 3 or 4, I think they're going to be very similar. 4 is going to be all trues, which is one possible way that occurs. And then here, this is 3 trues, right? Yeah. True, true, true. It's going to be the same. It's going to be 4 again. And how y'all doing today? Hope you're doing okay. All right. So 6 was the number of successful, favorable ways this could occur, but I need to know the total possible outcomes, right? So how many possible outcomes was this? 1 plus 4 is 5, plus 6 is 11, plus another 5 is 16 ways that whole event could occur. And so the probability will be the number of successes over the total number of outcomes. And so the probability, hey, quiet bud, 6 over 16 equals 3/8, which is the same as 37.5 All right, and so getting a 50% is a 37.5% chance for this student. Let's see. The sum of all the probabilities of all outcomes in a sample space is 1. All right, 100%, right? So probability of all of these possible events kind of occurring, it's got to add up to 100%. There's not some like secret mystery outcome that we didn't list. And so when you know the probability of event A, you can find the probability of the complement of event A in this little trick. So the complement of event A consists of all outcomes that are not in A and is denoted by this little A not A. I'll call it A bar. You can use the following notation. Boom. So the probability of not A is just going to be the 100%. Take away the probability of event A occurring. Right? That makes sense. That makes sense. All right. So here we go. Here we go. When 2 6-sided dice are rolled, there are 36 possible outcomes, right? 2 1s, a 2 and a 1, a 1 and a 2, etc. Okay? Let's see. Find the probability of each event. So for part A, the probability that the sum is not 6. Well, let me actually, you know what? I'm gonna screenshot this so I can scribble this up twice. That sounds helpful to me. So successes. Well, I'm gonna find the probability that the sum is 6. So that would be like a 1 and a 5. A 2 and a 4. Oh, it looks like this diagonal's doing it. Is it just this diagonal? All right, of which there are 1, 2, 3, 4, 5 possible outcomes. And so if the probability of equaling 6, I could write it that way. So probability of sum 6 would have equaled 5 out of 36. Then the probability of sum not 6, I could have denoted by 1 minus 5/36, which, by the way, is the same as 36 over 36 is the same as that, right? Common denominator and all that. Yep. And so 31/36 would be the probability of not having a sum of 6, which, by the way, is equal to 86.1 repeating percent. If you are wondering. All right, the sum is less than or equal to 9. Okay. Well, I'm going to I'm not going to use complements, although they say I should or could, but I don't know. My brain's not thinking that way right now. So I guess like greater than 9 would be the other way to do it. Okay. So let's see here. This is a sum of 7, sum of 8, sum of 9, sum of 10, 11, or 12. So less than or equal to 9. So this was, 3 and 6 was 9, 4 and 5, 5 and 4, and that one. Well, I guess the reason maybe you'd use a complement is because there were fewer of these than there were of all the rest. And so maybe it's easier to add up. So the probability of greater than 9 is equal to 1, 2, 3, 4, 5, 6. 6 out of 36. Which, by the way, equals 1/6. And so the probability of less than or equal to 9 will just be 1 minus 1/6, which is 5/6. By the way, it's Mr. Waddy's least favorite number, 5/6, because you have to say this. It's annoying. So this is 83.3 repeating percent. Boom, got him. All right. I'm gonna keep rolling. Here we go. Probability of not A would just be 1 minus 0.45, so that's 0.55. Right, 1/4. Its complement would be 3/4. The complement of 1 would be 0. Complement of that would be 0.97. Boom. All right, not bad, not bad. Here's a little bit of geometry for you. You're going to have to remember a formula from back in the day. Likely this formula, A equals pi r squared for the area of a circle. Area of a square is equal to side squared. We've got, let's see, you throw a dart at the board shown, your dart is equally likely to hit any point inside the board. And so this is kind of like a bit of a presumptuous thing, right? Like if someone's throwing darts at the board, hopefully they have some skill, and hopefully they're more likely to get towards the middle than they are anywhere on the board. Also, if you're me throwing darts, you might throw it off the board, right? That's also a possibility. But so we're pretending that the dart has an equal chance of landing anywhere inside the board. Are you more likely to get 10 points or 0 points? So let's find the area. Let's see, I'm going to need the area for 10 points. So let's see, so probability of 10. I'm going to need the area, so 10, so my success would be this area. So that would be pi times, and now 10 is the number of points, but notice 3 inches is the length of this radius. So pi times 3 squared. That would be the area of the successful region over the entire region, which is the square board. Okay. And the dimensions of this, if this is 3 plus 3 plus 3 is 9, and that's halfway across the square, so that is an 18 by 18 square. So 18 squared is the outcome. So let's see, so up top I get, I guess I'm gonna go decimals here anyway. 9 pi doesn't really help me. And anyway, so 28.27 divided by 18 squared. I'm getting 0.0. I guess I could convert this to a percentage. Shift the decimal place. I'm going to call that 8.7. And I got to round up to 3%. Boom. All right. Now the probability of... What's the other one? 0? Now this one... This is going to require me to do some fancy geometry. So the, oh, I could use a complement. That's interesting. This actually works a couple different ways. I could find the area of these regions by doing the area of the square minus the circle will equal, right, the area of that. I also could find the area of just the circle, and the entire circle, and then use the complement to get there. So a couple different ways, and they're both actually doing very similar math. Interessante. So I feel like doing this. This one's 18 squared minus this big circle has a radius of 9. So that's pi times 9 squared. And 324 minus 81 pi is 254.47 roughly. And so that's equal to, and I guess I'll write this in green. What's that? 324 minus second answer. And so I'm getting 69.53. And so this is the area of these little crusty pieces there, the leftovers, in square inches. And the total possible region is still the same. And so this is equal to 21.46%. And so you're more likely to get a 0 because the probability was greater. So more likely, let's see, likelihood has the I, boom, to get a 0. Assuming you have somewhat no skill, right? Okay, so that's theoretic probability, in which you can use actual outcome sample spaces and successful ways and predict it that way. Another way is using experimental probability, which is, I guess, like, in my mind, it's the less accurate one. It takes a lot more attempts to try to get a predictable outcome. It's a little, gonna have a greater chance of not actually representing reality perfectly. But anyways, experimental probability is based on repeated trials of a probability experiment. The number of trials is the number of times the probability experiment is performed. Each trial in which a favorable outcome occurs is called a success, etc., etc. And so you do the number of successes, right? Similar to what we were describing before, divided by the total number of trials. And so here they've got, like, in example 5, let's say you got a little spinner, woo, and it's got the same area for each of those. That seems to be true. The spinner was spun 20 times. Aha, so that's going to be our number of trials. So that'll be my denominator. Oh, wait, I don't think I even need that here, based on this question, if I recall. For which color is the experimental probability of stopping on the color the same as the theoretical probability? Aha. And so, notice, right, if I wanted the probability of red, here's the theoretical, 5 out of 20 is equal to 1/4, or 25%, which happens to also be the probability of red experimental, where this is 1 out of 4 areas they had all the same, right, is 1/4 equals 25%. And so happens to be red. Red had the same. But if I continued to experiment, right, and kept spinning, maybe these values would slowly fluctuate. And now there's an interesting thing, the way the universe tends to work, is that the more trials you do, over time, your results will approach the theoretical probability. So if I did this experiment 1,000 times, or 1,000,000 times, or 1,000,000,000 times, it will get closer and closer to the experimental outcomes. The converse of that is also true. If I don't have a lot of trials, it's possible to get much more exaggerated outcomes, values that are further from the expected theoretical value. Which color is stopping greater than the theoretical probability? That was the green, because 9 out of 20, what's that? I feel like it's going to be like 4 or 5 or something like that. What am I? Oh, boom. Got him. So yeah, that's 45%. Boom. Nice, nice. Okay, last example. Here we go. Video's almost done. In the United States, a survey, blah, of adults, blah, found blah have one pet. Boom, at least one pet. What is the probability that a pet-owning adult chosen at random, that's still key, has a dog? Okay? And now, if you take our statistics class here at BUHS, or actually anywhere, this at random becomes the hard thing to do with experimental probability. Like if you were randomly, quote-unquote, asking adults outside of Petco, what number of you have a pet, you're going to get messed up data because you didn't do a good sample, right? Because people outside of Petco probably have a greater likelihood of having pets than people found elsewhere. So let's see, what is the probability that they have a dog? So success in this case is 916. And I've got to divide by the total. And so that's not 1,000, by the way. The total will be the sum of all of these. All right, get ready for some dramatic calculator button pressing. 916 plus 677 plus 146 plus 93. And I get 1832. And so, probability of a dog. I'm getting 50%. Wow, that's actually quite convenient. Yeah, probability that a pet-owning adult. Yeah, so we already restricted this quite a bit. But anyways, yeah, so there you go. All right, I think I'm good. I'm good. Have a good day, everybody. Take care.